Henry Darcy, whose image is shown on the medal bearing his name, is the father of hydrogeology. His experiments showing the relationship between the hydraulic head and groundwater discharge allowed hydrologists for the first time to make accurate predictions of the direction and speed of groundwater flow. This is Darcy's law, a vector differential equation. In a nutshell, it says that the direction and magnitude of the groundwater flow, given by the q vector, depends on how the hydraulic head, given by the symbol h, changes. Notice that it doesn't say that the flow depends on pressure, which is what most people think. As we'll show later, pressure is one of the components of head, but it's not the sole or even main determinant of groundwater flow. Groundwater flows in response to changes in head, not pressure. Well, what is head? First, head is a scalar value with dimensions of length that varies with position. That is to say, there's a value of head associated with every location below the water table. For example, here we've identified the value of head at a whole lot of locations in the groundwater system. Each of these values corresponds to some unit of length, maybe feet or maybe meters. If we know how these heads are arranged, we can determine the direction of groundwater flow using Darcy's law. Darcy's law simply says that groundwater flows from high head to low head. For example, along the flow path shown here, the head decreases from 22 feet at the beginning to 13 feet at the end. This would be sufficient if we were dealing with flow along a line, but in 2 or 3 dimensions it becomes a bit more complicated. Consider the problem of knowing where the flow will go that starts at the point shown here, with the head at 20 feet. If we probe the area around our point, we find that the head varies considerably, and there are several directions in which the head will decrease. Which one is the right one? The answer is that groundwater will flow in the direction in which the head decreases most rapidly. Mathematically, this direction is known as the negative of the gradient, where the gradient is defined as a vector that points in the direction in which head increases most rapidly with a magnitude equal to that rate of increase. The gradient is indicated with the upside down triangle symbol. We often say that groundwater flows down the gradient, and we simply mean that it flows in the direction exactly opposite the gradient. So in summary then, Darcy's law says that groundwater flows from high head to low head, and specifically in a direction that is down the gradient, in the direction opposite to that of the gradient of head. Darcy's law also says that the velocity of groundwater flow depends on 2 things, the magnitude of the gradient and the permeability of the sediment. If the gradient is 0, there is no flow. If the medium has a high permeability, like sand or gravel, then the velocity will be relatively high. If the medium has a low permeability, like silt or clay, then the velocity will be relatively low. To understand how head is measured, consider an old-fashioned mercury thermometer. The thermometer consists of a glass tube with a very thin bore attached to a metal bulb which contains a reservoir of mercury. When the bulb is heated up under your tongue or wherever, it causes the mercury to expand into the narrow bore. You then read the temperature by the level of mercury in the glass tube. Head is measured with a similar device called a piezometer. Like a mercury thermometer, the piezometer has a business end where the head is actually sensed, and the rest of the device is just used for making measurements. In the case of the piezometer, the business end isn't a bulb, but a small opening in an otherwise enclosed tube. Water can only enter the piezometer through the small opening at the bottom. In practice, often the opening isn't so much as a hole as a series of very small slits cut into PVC pipe. Head is defined as the elevation to which water rises in a piezometer, measured relative to some horizontal datum elevation. Often we choose sea level as the datum elevation, but we don't have to. As long as all measurements in an area are made from the same datum, we can use heads to calculate the direction and velocity of groundwater flow. Here's an example. We place a piezometer into the ground as shown here. Water enters the piezometer through the input port and fills the tube to a certain level. The head is defined as the elevation of this water above datum. If this elevation is 15 feet, then the head at the location of the input port is 15 feet above sea level. Using piezometers, we can determine the head anywhere in the saturated zone. For example, here it's 20 feet above sea level. and here it's 15 feet above sea level. Groundwater will generally thus flow from right to left, though the exact path of groundwater between these points depends on the other surrounding head since it has to go down the gradient. I've shown this slide to make a couple points. First, the datum doesn't have to be sea level. Sometimes it's more convenient to use a local datum, which is just fine as long as all head measurements are measured from the same one. Second, saying that the water moves down the gradient doesn't mean that the water moves downward. In this example, it's actually moving upward, always in the direction of decreasing head. And now a little theory. We can show that the head, as measured in dimensions of length, is actually a measure of energy per unit weight. The total mechanical energy per unit weight is given the symbol H sub T and can be expressed as the sum of three energy terms: a gravitational potential energy term, an elastic pressure energy term, and a kinetic energy term. Notice that the kinetic energy term involves the velocity squared, and since groundwater velocities are so small, on the order of just centimeters per day, this term is insignificant and is dropped. That leaves us with our expression for hydraulic head. H equals Z plus P over rho G. The Z is the elevation of the water above datum and represents the contributions of the gravitational potential energy. And the P over rho G is the pressure of the column of water in the piezometer and represents the contribution of elastic energy. It's easier to see the components of head if we look at how it's actually measured. Once again, the head is the elevation of water in the piezometer measured relative to datum. The head can be deconstructed into two lengths: the elevation of the entry port above datum, which is Z, and the height of the column of water in the piezometer, which is P over rho G. Thus, H equals Z plus P over rho G.